As an illustration for the Newton's method, consider the following equation. e to x plus x minus 2 is equal to 0. Usually, when we have an equation where the unknown x appears only once, we usually can find the exact solution analytically. But in cases where x appears, say, in some polynomial and in the exponent, or as an argument of some other function like sine or logarithm, we usually cannot find the exact analytical solution. Then we have to be happy with the approximate numerical solution, and one way to get such a solution is the Newton's method. Before we apply the Newton's method, it's a good idea to play a little with the equation, to rearrange the terms, and then using some graphical approach, some graphical method to estimate whether the equation has a solution at all, how many solutions there are, and to guess the position of the solutions. So before we try the Newton's method, let's rearrange this function, this equation, in the form e to x is equal to, and we subtract x and add 2, we have 2 minus x. This is a convenient form for the graphical approach, because here we have two functions, and it will be easy to sketch the graph, and then the solution to the equation is the intersection of these two graphs. Namely, e to x looks like that. This is the left-hand side. And 2 minus x looks like that. This is the right-hand side of the equation. And the solution to this equation corresponds to the intersection of these two curves. And we see clearly that the two curves do intersect, so the equation has a solution. And there is exactly one intersection, so there is exactly one solution. That's a very important information. And we can guess the value, the x coordinate, the solution is definitely positive, and somewhere between 0 and 2. So we can now use the Newton's method, namely we denote the left-hand side as f. So now we go back to the form of the equation, something equal to 0. Well, we see that the function is defined and continuous for all real x. This is the best case. So we can say f is continuous in entire R. The set of all continuous functions is a very important object, so important that it has its name, namely C. So we can write f is from CR. Well, the letter C is dangerous. It may denote a constant, it may denote a set of complex numbers, but this time this denotes a set of continuous functions in some interval. This C comes from this C, continuous. These two lines are equivalent. If you don't like this, you can write it in simple words, continuous function. And then we want to find two values where the function changes its sign. That means the endpoints of an interval where there is the solution. Well, and we can use this picture. We know that the solution will be somewhere between 0 and 2. So we can choose A is 0 and B is 2. Because then the function value at A, namely at 0, is e to 0, which is 1, plus 0 minus 2, which is minus 1, negative. And function value at B, if x is 2, we have e squared plus 2 minus 2, so this is e squared, and this is technically positive. So we are happy to have two x values where the function gives opposite signs. So from the fact that the function is continuous and changes the sign, there must be some root. Well, we don't have to do it when we have the picture, right? But if we don't have the graph, this is the correct approach how to be sure that there is a root. Next, we want to exclude more roots, which we know that there are no more roots from the picture, but just to practice the formal approach, we compute the derivative of f, which is e to x plus 1 minus 0. We want the derivative not to change sign, but this is okay because this is definitely positive. Actually, it's more than 1. So it does not change the sign. That means the function does not change the behavior from increasing to decreasing, and we are sure there is just exactly one root. Then we want the second derivative not to change the sign. The second derivative is the derivative of the first derivative, which is e to x, which is also definitely positive, so never 0, so no S shape, so no dangerous situation for the Newton's method. And now the question is whether the initial approximation should be A or B. And we choose such endpoint so that the sign of the second derivative and the function value is the same. The second derivative is positive, the function value is positive for B, so we take x0 is B. That is 2. And we can start the actual computation. Let me quickly derive the Newton's method once again. If we have a function that crosses the x-axis and we want to find this point, starting with some initial approximation x0, then we consider the tangent line, and where the tangent line crosses the x-axis, we call this the point x1, and this is the better approximation to the root. And from this right triangle, we can express the tangent of this angle in two ways, either as the derivative or as the ratio of the function value denoted by the difference x0 minus x1. So x0 minus x1 is function value at x0 divided by the derivative, and so the next approximation x1 is x0 minus this fraction f at x0 divided by the derivative of x0. If you remember this formula, you don't have to derive the formula in the test. But this is the advantage of mathematics, that you don't have to remember almost anything. Everything can be derived just on the fly. Well, and now we know that x0 is 2. Function value at 2 is e squared. And the derivative at 2 is e squared plus 1. And that's it. This is the next approximation. For the purpose of the test in mathematics, this is perfectly okay, and this is all. This is the result. Well, if we really need the solution or a nice approximation of the solution, then we would use the same formula to compute x2, x3, x4, x5, possibly on some computer, and then after just a few iterations, after just a few steps, the results will be almost the same, the points, the x values will be almost the same, and that's the good approximation to the solution. Well, if you like, you can simplify this fraction a little, if you really like. that would be d squared plus 1. And now we have 2 d squared plus 2 minus d squared, which is so 2 d squared plus 2 minus d squared, which is d squared plus 2 divided by d squared plus 1. Ooh, no. Yeah, some number close to 1. Yeah, and we could compute on and on to get a better approximation. Now, when we know the Newton's method and when we know the Taylor polynomial, let me tell you a few more details about the Newton's method. Alternative derivation of this formula is by replacing the complicated equation with a simpler equation, namely T1. But this is actually the same as replacing the curve with the straight line, replacing the function f with Taylor polynomial of order 1. The graph of f is this line, and the graph of t is this straight line, the tangent line. And the tangent line, the polynomial is f x 0 plus the derivative times x minus x 0. This is T1, Taylor polynomial of order 1. Good approximation to the original function f. And we want to solve this equation. But this is a linear equation. X is only multiplied by a constant and added some constant. So this will be easy to solve. We first subtract fx 0. And then we divide by the derivative, and we have minus fx 0 divided by the derivative. And from this we can find x, the solution to this simplified equation, namely x 0 minus fx 0 divided by f derivative. And this is the same formula as here, just derived by a slightly different way. But the main idea is there, the same. This is the same. This second approach has the advantage that we will make use of in the next semester, where we will use the Newton's method for a system of equations. If we have not one, but 2 or more independent variables, 2 or more unknowns, and 2 or more equations, then we can consider x and f instead a scalar quantity be a vector quantity. And this gives the advantage of the Newton's method. It can be used to solve systems of equations. This is a very strong advantage as opposed to the bisection method. This is not easy to generalize for a system of equations. And one more remark to the Newton's method. If you consider this relation, or in a more general situation, that the n+1 approximation is equal to the nth approximation minus this correction f at xn divided by the derivative f prime at xn. So we have some formula, some function, some expression where we put xn, and the result is xn plus 1. If we call this expression g, then we can write the result of the Newton's method that the next approximation x sub n plus 1 is some formula, some result g at xn. And this is called iteration. That means we apply the function on and on to one original value x0 in this case. That means starting with the initial approximation x0, we compute x1 to be g at x0, and then we compute x2 to be g at x1, and then we compute x3 to be g at x2, and so on. So we must choose some initial approximation x0. We are given the function f from the equation. We find the derivative, and knowing f and f derivative, we can build this expression x minus fx divided by f derivative x, and we call this a new function g. So don't be confused. At this point, we have two functions. Function f, the left-hand side of the equation, and function g built in this way. Let me write it once again. What is g? G at x is x minus fraction f at x divided by f derivative at x. So once again, we have the equation fx is 0. We build this new expression x minus f divided by f derivative. We call it g. And this is a new, our working function. And this is good because when we iterate g, and we apply g to the previous approximation to get the next approximation, we can compute an infinite sequence of points with the property that they converge to the correct solution, g. So let us play a little with this iteration, namely when we apply g on and on. Iteration is actually composition of the function with itself, because we can write this as g at x0. So if you like, it can be written as g composed with g at x0. And similarly, this is g at g at x0, which is g composed, this time 3 times, evaluated at x0. So we compose the function with itself. So let's have a look at what happens if we have some function g and we iterate the function. First, if g is a constant, this is too weak. If g is a constant, then starting with any x0, any x1 is g, which is the constant, and x2 is g at c, which is again a constant. So the sequence is this constant sequence up to the first value x0, which is completely irrelevant because it influences nothing. Okay, too simple. So simple it looks almost stupid. Consider another case, say g of x being x itself. What happens when we iterate such a simple function? G of x is x. The graph is this line with the slope 45 degrees. Then starting with any value x0, x1 is g at x0, which is the same as the argument. The function value of g is the argument itself, so g x0 is x0. Similarly, x2 will be g of x0, which is again x0. So we have a constant sequence. Again, too simple, too stupid. But just to know what may happen, what if we have gx being x half? This is the axis of the first quadrant, and x half looks like that. Starting with some initial value, say 1, as an example. Then x1 will be 1/2 of 1, which is 1/2. Then x2 will be 1/2 of 1/2, which is 1/4. x3 will be 1/8. In each step, we divide the value by 2. So if it was positive, we decrease the value down to 0. If it was negative, we increase the value up to 0. If x0 were 0 exactly in the beginning, then it stays 0 forever. So we can say that 0 is a fixed point because it does not change with the function g. And this point is stable in the sense that if you go away from 0 in the initial value, then during the iteration you approached 0 back again. If we have, on the other hand, g being 2x, which is a graph like that, then starting with x0 is 1, we increase the value in each step. We multiply by 2 in each step, in each iteration. So starting with a positive value, we go away, we go to positive infinity. Starting with a negative value, we would go to negative infinity. And starting with 0, we stay at 0 exactly. Because if x0 is 0, multiplied by 2 does not change the value, still 0. So 0 is again a fixed point of this map, of this function, of this dynamical system, if you like. But this time 0 is unstable. Any deviation, small or large, to the right or to the left, will result in going away. If you start with some positive number, you go away to positive, and if with negative, you go away to negative values. In general, if the graph of f looks like that, for example, the graph of g, then the intersections with this line, y is equal to x, are the fixed points of g. By a fixed point, we mean a value that is not changed when applied by the applied function g. So these intersections of the graph of g with this line are the fixed point. If you start with x0 equal to this or equal to this, applying g does not change the value, and you have a constant sequence, x0, 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 it repeats on and on. What about the stability of this fixed point? If the curve if the graph of the function crosses this line in some small angle, like here, then this fixed point is stable. The iterations go closer to this point. If it has a greater derivative, if the angle is greater than 45 degrees, then it goes away. This can be expressed graphically by the following procedure. If you have some initial value, then applying g means we find the height of this point on the line. And then we want this value, this output, this y value, to use as the input, as the x value in the next step. So to have this distance on the x-axis, we just go to this line. And then we go to the graph of the function. Because at this x we want the result. And then we want this result to use as x, so we go to this line. And then we go to the graph, to this line, to the graph, to this line, and so on. And using this zigzag line, we can simulate the iteration xn plus 1 is equal to g at xn. These vertical segments correspond to the function value, to applying the function, because from some x we find the function value, the point on the graph of g. And these horizontal steps, these horizontal segments, make the change that what was the result in the previous step is the input in the next step. Swapping x and y, or using the old y as the new x, using the old result as the new input. If the derivative is negative, then from initial x we find a point on the graph, and then we find a point on this line, and then we find a point on the graph and on this line. So when the derivative is negative, we oscillate around the fixed point. If the derivative is negative and small, then we approach the stable fixed point. If the derivative were negative and larger than 1 in absolute value, we would depart away from the fixed point. So let's have a look what is the derivative of g corresponding to the Newton's method. This will be an important question. Whether the Newton's method is stable or not. So let us find the derivative of this function g. G prime at x will be, derivative of x is 1 minus fraction, and we know how to differentiate the fraction. We take the square of the denominator. This prime means derivative, and this 2 means the square, second power. And then in the numerator, we have, well, to repeat the derivative of the fraction, u derivative v minus uv derivative divided by v squared. So we have u derivative. U is f, so we have f derivative times v, which is f derivative, minus u, which is f, and v derivative, which is derivative of f derivative, which is f second. And we are interested